We did not label all the arrows, correct? There are 4 arrows. So I'm going to give you guys a minute right now. If you didn't label them, I want you to at least mentally label them before I show you, because this kind of gives you the answer. Okay? So open up your notes. Look at that diagram from yesterday, Charlie. Look at that diagram.
How does it?
From yesterday. What we wrote down on the board. There you go. So those arrows, those 4 arrows, try and label those, or again, at least mentally. I'll stop the video and show you. So you got alpha, beta, gamma, positron, right? And you got arrow number 1, which bends up towards the positive. You got arrow number 2, which goes straight through, undeflected by the positive or negative. And then you got arrows 3 and 4. Both of them bend down towards the negative, but one of them bends more than the other. So think about that, right? Alpha, beta, gamma, positron. What makes sense to you based on the charges, right? Alpha's positive, beta's negative, gamma's neutral, and a positron's positive. So maybe you did this yesterday. I'm just giving you a little time right now while I'm talking to at least label them mentally. I'm going to play the video now. That should be good enough. You should either have an idea or you don't. And this only has 3 of them now, beta, gamma, and alpha. So I'll talk more specifically about positron after this. Okay, so it's only 1:44. We'll finish this up, and then we'll go over the homework, and then we'll take some more notes. Cool.
British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays.
How come alpha isn't deflected as far as beta is? In other words, alpha, from going straight, it only deflects a little bit, but beta goes up further from the straight path. Why would beta be deflected more than alpha? Say it again?
It's smaller.
What's smaller? Beta?
Yeah.
Yes, very good. It's the mass. Beta is 0 over, I don't need to write it, that's on table O. Beta is 0 over -1e. Alpha is 4 over 2he. Alpha is more massive. So it's harder for the electric field to deflect it because it weighs more, right? I mean, you can think of an analogy of like pushing something. Pushing something that's really heavy, maybe you can push it a little bit. But something that's light, you can push it further. Same kind of concept here. So the light one is deflected more. So keep that in mind for arrows 3 and 4, right? On our notes, 3 and 4. So what's the one in the middle? What's the one that goes straight through, doesn't get deflected at all? Gamma, because it has no charge.
Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays.
So it makes me laugh because she's like, this is due to the energies of the relative blah, 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 blah. And it's like, you guys are like, what is she saying? It's confusing to me how she words that. I mean, I understand what she's saying, but it's very convoluted. Basically, it's just heavier, okay? And there's less energy associated with it. I wish I had alpha to show you on the thing here, but I don't. It went through all of its half-lives, actually, so it doesn't give off any emission really anymore, not hardly at all. So it wouldn't be a very good demo. So anyways, the point is, alpha is positive, it's attracted to the negative, deflected towards the negative is how the regents words it. Beta is deflected towards the positive, and gamma goes straight through. But Brady, lights please. Yesterday we had 2 arrows, right? So here's our, what do we have down here? Negative or positive, right? Negative, right. So we had one that was like this, that was 4, and then 3 kind of went like this. So number 1 was beta, that went up top. Number 2 was the gamma, right? Number 2 was gamma. Here's our positive. And number 1, so beta, gamma goes straight through. What's 3 and what's 4? Based on what that thing just showed you and what I just said about the mass. Which one gets deflected more? Which one gets pulled in closer to the negative? The heavier one or the lighter one? Based on what you just saw. Lighter one. So this is going to be your positron. It can bend more because it's lighter. The heavier one doesn't deflect as well. So this is going to be alpha. Okay? And then number 2 is the 0 over 0 little Y looking thing. I don't know how to draw that. So that's your gamma. So gamma is undeflected. Alpha and positron both towards the negative, and then beta goes up towards the positive. Out of these 3, which one is the, or 4, which one is the most penetrating? In other words, what would go right through us? Gamma. Okay, which one's the least penetrating?
Beta.
The one that bounced off the paper in the video yesterday. Alpha. Alpha's the biggest. Didn't I use the analogy in here? Trying to put my finger through my arm versus a needle?
Yeah,
Right?
yes.
I mean, which is kind of weird, but bigger won't work. Smaller will, right? So bigger, the bigger it is, the less penetrating. The smaller it is, gamma is actually smaller than these 2. So just keep that in mind. All right, so we're done with that. Let's go to the homework now. Okay, number 61. Who's it going to be? How about Zach? Tell me, how many neutrons does neon 10 have? So in that chart.
9.
9 neutrons, very good. So what he did, I'm just going to kind of hold it up. If you look at neon here and go left, it tells you the number of neutrons. So number 9, or 9 neutrons for neon, very good. What's the mass number, Isla? 19, very good. How'd you get that? 10 plus 9, very good. So neon 19, atomic number 10, has 9 neutrons, right? We just said that. And it has 10 protons because that's the atomic number. So the mass number comes from adding those together. Who put 20? Thanks for being honest. Why'd you guys put 20? I'm not like young yet. I'm using this as an example of a common mistake. So it's okay. This is normal. It happens all the time.
That was the mass on the
Right, that's the mass on the chart. You got to be careful with these nuclear questions. If they give you information, use the information. So this has 9 neutrons and 10 protons. So 9 plus 10, the mass is 19. The one on the chart is 20. This is a different isotope of neon. So they're not talking about that neon over there. That's neon 20 over 10, which has 10 neutrons, 10 protons. This is not radioactive. Why? 1-to-1 ratio. This is not a 1-to-1 ratio, so it's slightly unstable. So that was a trick question. So it looks kind of easy, right? I'll fill in the chart, get a point. But it's common to make mistakes with the 20. So if you made a mistake, no big deal. But just understand where that 19 came from. Adding those 2 together, and that's from here, not up there. All right, and the last thing would be neon 19. You would write Ne-19. Ne-19. That would be the last box there. 62, the answer is because it has a neutron to proton ratio 1-to-1. S32 is stable because it has a neutron to proton ratio of 1-to-1. Where it says, and if you're daydreaming right now, stop it, pay attention, focus. 62, it says, explain in terms of atomic particles why S32 is a stable nucleid. These are atomic particles, protons, neutrons, electrons. So you had to talk about them. So you had to say the neutron-proton ratio is 1-to-1. Or you had to say it has the same number of neutrons and protons. That would work too for 62. All right, 63. Who can tell me the neutron to proton ratio for nitrogen? How about Blake?
18 to 10.
Say it again.
18 to 10.
let's try again. Go to nitrogen on the grid for me. And if you got, well, you don't know if you got this wrong yet, but everyone go to the grid. Everyone find nitrogen. Blake's going to tell me, according to that grid there, that graph, if you go straight, we'll go to the left of nitrogen and hit the y-axis. How many neutrons?
7.
Try again.
Wait, what?
Go to nitrogen and move left till you hit the y-axis. So your finger pens on that dot where it says N.
Yeah.
And then just stay on that line and move straight to the left. You should be one line underneath 10.
9.
You see, it's hard because I'm not showing you. But you follow me now?
Yeah.
Okay, so you got 9 neutrons. Good job. Go back to nitrogen and go straight down. What number are you on now for the protons? 7. Very good. So the answer is 9 to 7. This question gets confusing because kids forget where to look or don't know how to read that graph, which is fine. This is why we're practicing. So neutron to protons, 9 to 7. I'll be honest with you. Who put 7 to 9? Honest, I'm faking out there. Honest mistake. It says neutron to proton, so we would need neutron first, proton second. If they said proton to neutron, it would be 7 to 9. You may think it's the same, but just be careful with the wording. That's a common mistake too. Questions with that? So we're good, Blake, with that? Okay. 64. All right. If you watch the video, I think even within the first minute, you should have figured it out. 14 over 7, no, 16. 16 over 7n. Yields blank plus blank. This is what we're going to be putting in our notes here in about a minute or so. Anyone tell me how to fill in the blanks there? What do we put? Go ahead, Nicole. Put it all together.
O with 16 over 8.
I'm going to put that here. Oxygen, 16 over 8. Good.
And the B thing,
Yep.
minus.
Good. I'm going to do this instead. Very good. That's exactly how you do it. This is a beta particle, and here's what you need to learn today. So we still got about 12 minutes left. So in our notes, we're going to be writing these down. But let me finish going over this. This is called natural decay. Nitrogen 16 naturally decays on its own, just like these are naturally decaying. I don't have to turn them on. I don't have to do anything. They just naturally give off radiation. This also naturally gives off radiation. Here's the radiation it gives off, beta. How do I know that? Here's how you know. Go to table N, please. This is why I had you take these out. Go to table N. I want you to find this isotope, N16. Find it on table N. So go to table N. Everybody find N16 on table N. If you can't find it, please let me know.
On what?
Table N. Find nitrogen 16, N16. N-16.
Seconds.
You got it? Brian?
Yeah.
Okay, everyone look all the way to the right, under the column that says decay mode. Devin, what do you see? Oh, it's not all the way to the right, I'm sorry. But it's a B minus. And B minus on table O is what? Go to table O now. What's B minus? Beta. That's how I know to put that, because table N tells me. So I wrote myself a note to make sure we talked about it. You have to use table N to answer this question. You look this up, you find out it's beta decay, so you write, why is it called beta decay? Because it gives off a beta particle. You write this down in one of the blanks, and then in the other blank, you have to balance the numbers. What does that mean? Here's what that means. If I draw a line here, and that line's kind of like the middle part of scales, right? Think of scales. This side has a 16 on top, so this side needs 16 on top. 16 plus 0 is 16. That's balanced. If this has a 7 on the bottom, we need a 7 between these two numbers. So negative 1 plus 8, that's 7. So the bottom is balanced. So that's how we know what numbers go here. And then how do we know it's oxygen? Once you get that 8, you go over to your periodic table and say, who's number 8? That's oxygen. You write down oxygen. That's how you do these types of problems. We're going to do 3 more in our notes. I'm going to have you practice a little bit more tomorrow. We have a worksheet for homework, which is similar, but a little different. I'll explain by the time we get out of here. Yeah?
Never left really quick.
Yeah, real quick. You're going to be missing a lot of stuff here. All right, in the notes. Your notes should be out. You're writing down natural radioactive decay / transmutation. So this is called natural decay, natural radioactive decay, or natural transmutation. All of those mean the exact same thing. And there's 3 types, alpha, beta, and positron. So we're going to do alpha decay first. So you need to use table N here to help you out. So I want somebody, who's it going to be? Shelby Clickman. Go to table N and pick an isotope that gives off alpha particles. So you're looking for the alpha, which is like a weird looking fish type A. 239 PU 239. Here we go. So PU 239. Write that down. The atomic number for PU is over on the bottom there, number 94. So you write down your isotope from table N, and you draw an arrow. That means this is naturally breaking down, decaying into something else. That's what that arrow means. Then you're going to have 2 blanks. 1, 2, just like the homework. Now, Shelby told me, or I told Shelby to look for the alpha decay. So this particle here is going to be an alpha particle. This is why it's called alpha decay. It gives off an alpha particle. So, Evan, what is the formula or equation, not equation, notation for an alpha particle? Table O has it. Give me the notation. 4/2He. Very good. That's an alpha particle. Now, we got to fill in the blank. How do we do that? The numbers have to balance. So we have 94 on the bottom. We need 94 on the bottom over there. We have 239 here. We need 239 over there. So take a minute. See if you can figure out what element goes in the blank. If you've been watching, you should have a fighting chance here at least. Try and figure out what goes in the blank, and then I'll go over it. Numbers have to balance. Then once you get this bottom number here, you look it up on the periodic table. That's how you know the element. Might have to look near the bottom. And Shelby, what do you think? That's fair. Steph? Well, give me the numbers. 235, 92, you. Yeah, very good. Here's how she got that, so pay attention. Because the next 2 I'm going to go a little quicker to make sure we have enough time to go over what you need to do for the homework. 239 is the mass. So again, I do this sometimes just to mentally separate it. This side has to equal this side as far as the mass and the atomic number. They have to balance. So if we have 239 here, I need these 2 numbers to add up to 239. 235 plus 4 is 239. That's balanced. This is 94, so I need these 2 numbers to add up to 94. So 92 plus 2 is 94. That's why that's number 92, to give you 94, right? To balance. Now you look up 92 on the bottom, and it's U, uranium. So you just write in the U. Let's do another one. That's alpha decay, again, because it produces alpha. Jake, pick a beta decay from table N.
H3.
H3, all right. So H3, this is tritium. H3 over 1, arrow. This one's easier, maybe. Smaller numbers, for sure. H3 over 1, that's tritium. It decomposes, or I shouldn't use that word, sorry. That's a chemical word, not nuclear. Decays into a beta particle and something else. So if you look on table N, you should see a B minus next to this nucleid here, H3, and that means it's beta. 0, negative 1e goes in the first blank. Now again, do the math. Try and figure out what goes in the blank. And the winner is 10. Well, what's this going to be right here? It's going to be 3 on top. I think you said 3. Yep, 3 on top. Very good. 3 plus 0 equals 3. So what number here plus negative 1 equals 1?
2.
2. So now, who's number 2? Look up the element number 2. Helium. There you go. Very good. There it is. So that's beta decay because it gives off beta. Next, positron. Bree, pick a positron. Decay. From table N. Just pick one that goes through positron. K37. K37 over 19. Again, that 19 I'm getting from the periodic table, number 19. So it gives off a positron, which is 0 plus 1e. I'm going quick because you can look that up on table O. That's nothing you have to memorize. You just have to remember to look on table O. Now again, we do the math. I'm going to do this one real quick with you. 37. Now, if this is 19, this is plus 1, this has to be 18, and that's argon. So what happens is potassium emits positrons to become more stable and transmutates into argon. So this is transmutation naturally. This is occurring on its own. We're not forcing it to do anything. The next one, we're going to get one example before the bell, is called artificial transmutation. That's when scientists mess with stuff. So artificial radioactivity, this is called artificial transmutation. And this is more about your homework right here. Artificial transmutation. You guys ever hear of a particle accelerator? Anybody?
Where they slam them together?
Yeah. Take particles and they sometimes spin them or they get them going really, really, really fast, slam it into the nucleus of a radioactive isotope or not. It doesn't have to be. Usually it is. And the nucleus basically explodes kind of like bowling ball and some bowling pins. Okay, things start going crazy. And sometimes radiation is produced and a new substance is produced too. That's what this is. Nuclear power plants, nuclear fission reactions. That's this. We'll talk about that this week too. So let me give you one example and then I'll give you your homework. So let's take potassium, we'll go potassium 40 over 19. Let's hit it with a neutron. So what's happening here is this neutron is being used, and the word is bombard, to bombard the nucleus of potassium 40. What happens is it kind of breaks apart and gives off beta and something else. That something else is a new isotope, a new nucleus. That's why this is called transmutation. And it's artificial because we are slamming this into the potassium. We are doing it. We're bombarding K40 with a neutron to produce a new nucleus. And that's right here. And also we're giving off some radiation. And when we do the math, this is 40 plus 1, which is 41. The bottom number is 19 plus 0, so this has to be 20, because 20 plus negative 1 is 19. Number 20 is Ca. So I went very quickly, I realize that. But that's the same concept, but it's artificial because we're taking two particles and slamming them together. So we're doing that in a lab somewhere. Your homework is filling in the blanks, just like this. Just like that. Here's the worksheet coming back to you.
He's actually he's pressing.
Oh, I didn't do that.
Yeah.
Devin, you let me forget about that shirt, I'll be pissed. Because it's like literally sitting.
This is due tomorrow, and we'll be after school if you need help.
Are you leaving right after school?
You got one under your
What?
Steph, here. Who didn't get one?